Okay, maybe wait for a few minutes. Okay, wait for a second. Let me quickly. Okay, maybe we can start with. I think that the last question here. Okay. We can start with these questions, and let me give you maybe a few minutes to try. We have um, this is the picture. In the picture, uh, the, the region R. And the question is evaluate double integral of 3x plus 4y squared dA. Okay. So this is the circle of x squared plus y squared equal 1 and x squared plus y squared equal 9. Okay, perhaps let me go to the previous last discussion and before we solve the questions for today's uh, last questions. We have this questions: find the volume of solid. They are lies under this paraboloid and above xy plane and inside the cylinder x squared plus y squared equal to x. After we solve this and we simplify that this is, we can compute and convert to the polar curve, and we got the polar curve is this, and then we can write down that our radius is, or if we write down that the radius is between 0 and 2 cosine theta. Now, to determine the angle, we could start with 0 here. If we start with the 0, then one point that we get is pi over 2. Okay, so to make it into a full circle, we need to have negative pi over 2 for the other cases. Okay, so it doesn't need to be like, if we check with the theta from 0 to theta 2 pi, this will not at the point of our intersection. So that's why we are going to use pi over 2 and negative pi over 2. Or in our case, because of the symmetry, we could write 0 and pi over 2 and then multiply by 2. And then we get the result is 3 over 2 pi. Okay, I hope you can get the illustrations and understand what does it mean. Okay, now let's go to our questions. For the whole questions, number 1, 2, 3, you can also check the Moodle I attach as a PDF. Okay. Okay, I think we can start to solve this. Or anyone get the answer? Which one? A, B, C, or D? You can write in the chat box. Okay. Anyone calculate the answer? Okay. We'll wait for a few minutes. Okay, by the way, don't forget to check your Moodle. I'm working on the quiz, okay? Because I think only 2 students working on the quiz. Check the weeks on the Moodle, okay? And don't forget that there is a deadline for the quiz. If you forget to work on the quiz, I'm not sure. Well, I can take another one. Let me check the. Yeah, deadline is Wednesday. Deadline is Wednesday, and only 2 students so far working on it. Okay. Okay. Any solution for this one? Anyone get the answer? A, B, C, D. Uh, D. Yeah. Yeah. Correct. Okay. Let me solve this. Let me write the steps for you. It's correct. The D is the answer. So we could write down that we could write in terms of the radius and theta, and we could write down that if this is our polar, then we could have the theta from 0 to pi, and the radius is from this 1 and 3, right? 1 and 3. So we could write 1 and then 3, and I think it's not too difficult for the region here. So we could write down that this is 0 pi 1 3, and then the equations is 3x plus 4y squared. We could write in terms of polar, so we could write 3r cosine theta, and then plus 4 r squared sine squared theta. Don't forget to multiply with r dr d theta. Okay. Now we could write, or maybe we could just multiply with r first, and then we could integrate. We could integrate. Okay, we could integrate. Okay, sorry. Okay, we can continue here. So we integrate 0. It will be r cubed cos theta, and then this will be plus r power 4 sine squared theta, and this will be d theta, and this will be 1 3, right? And we impute the number. It should be 27 minus 1, 26 cos theta, plus 381 80 sine squared theta. And we still have d theta. Now we can integrate, and we can take the double angle formula for the sine squared. The total will be 26 sine theta from 0 to pi plus integration 0 pi 40 1 minus cos sine 2 theta, right? Now if we look here, this will be 0, right? And this will be goes to sine, right? And sine 0 and pi is 0, so we will have just 40 pi. Right? So that will be our answer, D. Okay, that would be our answer. Okay, so okay, and let me write here. Don't forget to work on quiz chapter 12 and 13. You can find on Moodle on week 16 and 22, I think. Or at least you can check now. You can check now. Make sure you found the link, and you can maybe later on tonight or maybe tomorrow still have time, and try to work on the quiz. Okay, because until now for this class there's just 2 students click the quiz and work on the quiz. Okay. Okay. Okay, I think we can continue to the next sections, which is this is 15.3. Okay, double integral in polar. Now we can continue to so this is 15.3. Let me write 15.4. We skip. Okay, this will be about the mass, center of mass, lamina. I will skip it for you, and we are focused on 15.5. This will be about the surface area. Okay. Maybe before we continue, is there any question for this part? Okay. The other two here, you can work on by yourself, and I think I also will include these two into additional video. Okay. Okay. Maybe any question first from the previous one? If not, then I will just continue. Okay. We know that that C, function of 2 variables, has a surface S. Okay. Where F is continuous partial derivatives. We know this from the beginning of chapter 15 and 14. Okay. And assume that the function is positive and domain D is rectangle. Okay, and let me go through which part here of this. I think we can start from the first one. Okay, so this is a surface, and imagine we have a rectangle at the bottom, the projection, and we are now slicing the rectangle and make it into small pieces like this one. This is the small pieces, and we project it back to the surface, and we see that we have this. If we compare, this is the real surface, right? The surface that we want to evaluate, and this is the projections of the rectangle. Okay. Now, if we look at, there are gap, right? There are gap. And if we remember what we have learned before, that is, this plane here is basically our t, our tangent, right? Let me write here, that is the tangent plane as to P. Okay, so from the surface to the point P, okay, is approximation to S near the P. And the delta of T, this is part of tangent plane that lies directly above the rectangle. RIG is an approximation to total area of S. So again, we see that this is approximations, okay, which means that we see that it has a small gap, okay, between the tangent plane to the area. So because it's a approximation, we are going to impute the Riemann sum of the area, which determines that it will have that is the delta Tij. We could also say that this is the parallelogram okay. Now we need to break down our formulations for the delta T. Okay. So we need to break down the delta T and make it into each of parts of the surface area. We need to write down, okay, to define, okay, to define the delta T. And we need to define through the partial derivative, okay, because it's a tangent plane, right? So we have a partial x, partial y. Okay. Now let me give you another illustrations to make it more clear. Okay, now let's focus on the delta t. So this is the delta t, and we break down the delta t to make sure that we simplify the equations. Okay, let's say we have a delta x here. Okay, the delta x for x-axis, delta y for y-axis, and from this point P, we have two vectors. Okay, vectors a and vectors b. Okay, so first we can write the definition for vector a and b. So let the vector a and b it's a vectors that start from point P ij and lies along the plane, right? The sides of the plane, or we say it's a delta t. Okay. Now from the vectors a and b, we know that the area of parallelogram, if you remember, so we can write area delta t is a cross b, and find the magnitude. Okay, and then another definition is partial x, xi, yj, and partial y, xi, yj. This is slopes of tangent lines through point P in direction A and B. So direction A is for the partial x, this is partial x, and B is partial y. The directions, they are the same directions. Now, because we have these definitions, then we can write down that the vector A, this will be delta xi plus the partial x let me maybe right on the left, maybe here a bit. So A is delta x I plus partial x xi yj delta x and then k, and then B is delta yj plus partial y okay. Okay, so because of this is the slopes in x, slopes, right? Right, this is the slopes. This is also slopes. Okay. And then we take the A cross B. This is delta x, this is 0, this is 0, this is delta y. K will be partial x delta x. This is partial y delta y. And take I, j. Okay. A cross B will be delta x delta y k minus delta y partial x delta x I plus delta x partial y delta y j. Okay, now we have all terms is delta x delta y delta x delta y, or let me write into more clear, that is partial x delta y I minus partial y delta x delta y j, and plus delta x delta y k. So we could factorize the delta x delta y. This will be delta a. Okay. That the delta x delta y is equal delta a. Okay. So this is a cross b, and then the delta t is equal magnitude value of the a cross b. Now we can input so partial x squared plus partial y squared plus 1 and delta a. Delta a. Okay, now from the definition here, from here we can write down that the area will be limit and we can write down all the partial x plus partial y plus 1 and delta, right, and delta a. And by the definition of the double integral, we can write down the area as double integrations d, this will be 1 plus, we could say dou z dou x partial x and dou z dou y for partial y, and this will be dA. You can also compare with the calculus 1, the surface area that we have in calculus 1. Let me write here. In calculus 1, the surface area is from A to B 1 plus. Now it's not only dy over dx, we have two partials, right? Okay, any questions? I think if you want just to focus on the finalized equations, which is this one, that's still okay. And how we are going to use this equations is, I think, not really that complicated. We just follow on. If you would like to find the surface area, the first thing we are going to do is we find the partials. We find partial x, partial y, and then we find the region, okay, the restriction for the integration. Okay, I think we can take this into examples, maybe 2 examples, and then we can move on to chapter 15.6, the triple integral. So the A is the area of the red part. Yes, yes. Actually, the area is this one, the blue one here, but we are going to approach through the red one. Okay. We approximate through the red one. Okay. Okay, let me give you some example on how we are going to use the area. So example, find surface area of C. Okay, that's the surface, and we are going to have lies above rectangular region in xy plane. So this is the restriction for the rectangle with vertices 0, 0, 1, 0, and 1, 1. So to solve this, first we need to draw the rectangle. Okay, not draw the whole surface, but we just need to draw the xy plane, especially. Usually that is the questions. So we are just going to draw very quickly here y-axis and x-axis. and probably we are going to have this is 0, this is 1. So we are going to have at 0, 0, at 1, 0, and 1, 1. So maybe 1, 1 is here. So this will be our region. Okay, this will be our region. Let's say the region is region T, okay, or R. Maybe just T or D. It's okay. So this is 1, 0. This is 1, 1. This is 0, 0. Okay, because it's a triangle, okay, it's not a fully rectangle. So because it's triangle, then we are going to define the distance, or define the value in the integral with some equation. So we know that this should be y equal x, right? So we could have that t. If you want to have x, this will be 0 to 1, and y will be from 0 to x. Right. Or if you want to make it from y is 0 to 1, and then you can make it x is from y to 1, and that's also okay. But let me just write this. Okay, let me just write this. So we write the function of two variables is x squared plus 2y plus 2. We could write each one, okay, for each partial x is 2x, partial y is 2. And then, I think because it's not too difficult to do the partials, we can directly write the area. So which this is square root of 2x squared plus 2 squared plus 1, and then dA. We could solve the inside. Or maybe we'll write 0, 1, and then what is 0x? 0x, and then square root of 4x squared plus 5. And then this will be dy dx. Now depends on, because again, we are going to have the double integrations. Now you need to be wise. Okay? You need to be wise on defining this dy dx or dx dy. Okay? Because you see that we have x here, I believe it will be very easy if we just do dy dx, okay, rather than dx dy. Okay. So we are going to do the dy, which is just adding y, and then it will be helping us to solve the whole integration. If you look at, this is becoming y, and then square root of 4x squared plus 5, and then 0x, and then the x. We put just x inside. We are going to have x integrations 4x squared plus 5 and the x. And because we know that this is x squared, this is just x, we can do some substitutions, right? We can do some substitutions. We can take the 4x squared plus 5. Wait, what is this? So this will be u substitutions. Du is 8x dx, so it will be 1 over 8. So it will be 1 over 8, and then should be square root of u. So u half plus 1, so 3 over 2, 2 over 3. 2 over 3, 4x squared plus 5, 3 over 2. And then it goes from 0 to 1. So this will be 1 over 12. 1 over 12. 4 plus 5 is 9. It's 27 minus 5 squared of 5. This will be the surface area. Okay. I believe the calculation for the double integrals, as long as you keep practicing and make sure that you are familiar with the double integral, I don't think this will be very difficult. Okay, for the calculations, the difficult one should be determine the very first setup for the integrations. That should be difficult. Okay, now other possibility for example is we just look on this example is just showing you that we just have one variable inside. Right? What we have if we have two variables? Now we can try to work on. Okay, I hope you guys finish this one and I can go to the next sections. Okay, we'll go to the next section. Next example. Find the area or find the surface area of the part of paraboloid that lies under the plane z equal 9. Okay, now we need to at least a little bit imagine what the paraboloid looks like. We know that this will be a circle, so it has a circular projection, and it has the positive paraboloid, which means that it should be goes like this one. Okay, so let's imagine that this is the plane. This is z equal 9. So you're projecting this circular into the area here, right? So this is your D, let's say D or R. So we could write some restrictions that we have. That is when z is equal 9, so we have x squared plus y squared is equal 9. Okay, this is z equal 9. And we could write down directly the area, or maybe just writing the formulations first. This should be 1 plus partial x squared plus partial y squared. Okay. This will be 1 plus 2x squared plus 2y squared. Yeah. And this could be 4x squared, 4y squared, right? So we could write down this should be 1 plus 4 x squared plus y squared. Yeah. Okay, now if we look at D, because it's a circle, and we have this equation, we have more simplification if we do the polar coordinates. Okay, so let's convert to polar. So in circle, we have the radius is from 0 to 3, and the theta is from 0 to 2 pi. So you could write down and change all with polar. So 0, 2 pi, 3, and this could be 1 plus 4. This will be 4r squared, and then r dr d theta. And we can do the substitutions. So let's do substitutions here. So 8r, so it would be 1 over 8. So 1 over 8, and then what else? So we will have square root of u. U is 3 over 2, 2 over 3, right? So 2 over 3, this is 1 plus 4r squared, and then 3 over 2 from 0 to 3, then d theta. And I think d theta we can directly write 2 pi. And there is nothing inside, right? No theta inside, so we can directly write 2 pi, and then this part will be 1 over 12, and this goes to 37, square root of 37. So 37, 37, right? And then minus 1. So we could have pi over 6. Okay, this will be the answer. Okay. 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 Any questions? No, then we can move on and discuss on triple integrals. Okay. Okay, I think we can move on. All right. Now this is 15.6. The triple integral okay, let's say on the first case we are going to have triple integrals over rectangular boxes. Let's say we have functions defined on B. So B is you say it's like a box, but let me just write B as definitions for each axis. So let's say we have now three variable x, y, z, and let's say we have a 2b for x, and then c 2d for y, and for z is r 2s. Okay. Okay. Now by doing this, we are looking at the volumetric, right? We are looking at the volume that is made up from x, y, and z. So if we would like to draw, let's draw. Well, let's start from the first one here. So let's start from here. So this is our B. So B is, you can imagine like a box. Right? Now the first step to approximate the volume is we are going to slice B into small boxes like this, right? So we slice into small boxes, and we can say that this boxes is delta y, or here is delta y, delta x, and delta z, right? Let me give you one more. So we are having these small boxes, and we could say that the small boxes, we could write down the small boxes I, j, k. This will be between the x I minus 1 x I, and then for the y is y I minus 1 y I, and for z, sorry, it's j, is I, j, and k. Okay. And of course, if we take the volume of the small box, we take it as a delta phi, which is delta x, delta y, and delta z. And then from this delta volume, we can make it into a triple Riemann sum. So from I, let's say this is L, J, this is M, this is K, and this is N, L, M, N. And we have functions x, I, j, y, oh, I, j, k now. Sorry, we have a triple, and then multiply with the delta formula. And of course, the sample, the ijk, yijk, and the z1, ijk, this is a sample points in the box ijk. Okay. Now, by the same analogy, we then get write down the definitions of the triple integrals as this is b f x y z, and this is dp equal limit, and then l m n goes to infinity of the triple Riemann sum This is ijk, yijk, cijk, and then delta volume. And provided the limit exists. Okay, provided the limit exists. Now, of course, from here we can also make it into a Fubini, okay, the Fubini theorem for this triple integral. So Fubini for triple integrals. So if f is continuous on rectangular box B, which is AB and then CD and then RS, we could write down triple integral. This is f x y z dx dy dz. So this will be RS, CD, and AB. And we can arrange the integrations as much as we want. We can arrange like dy, dz, dx, and we can just change the order of the integrations. Okay, I don't think this should be having a complex situations, because I believe since A, B, C, D, and RS, they are all constant. I think based on which integration you are going to do first, it should be not a problem. Okay? And just remember that whenever we have the integrations, if you feel that maybe it's not really going to be integrated very well, then you can change the order and find which one is easier. Okay? And for the Fubini, for the constant here, I think you can easily switch. Okay, any questions? So the difference with the double integral that we've done at the beginning of this chapter, the double integral, we have the surface, right? We have z equals some function of two variables, and we are going to multiply those and with the so we have the area and we have the height. The height is the functions, right? So area and height becomes the volume. But now, what we have here, we start with the volume. We start with the boundary is set to be a volume. Okay? We have some volume, okay? And then we slice, and we get the small boxes, and from those small boxes, we define that we will have triple Riemann sum, and triple Riemann sum of the function of three variables. So we directly have the function of three variables, okay, and we multiply with the dv to make it into the whole volume. If there's no questions, we can continue. Okay. So I believe for this one, I don't really need to give you some example because I think it's similar to what we have done in double integral. I think the most complicated one is the if the integrations have a functions, and that might be complicated. Okay, let me go to the next section. Okay, if there's no question, let me go to the next one. This will be the triple integrals over general regions. Okay, let me go to the picture in this one. Let me start with the first figure. Okay. Now we define the solid, okay, with two functions of two variables. Okay. So let me write here that this solid E is a solid with upper surface the z equal u2 xy and lower surface is z equal u1 xy. Okay, and then we have also d, so we have E and D. So D is projection of E on xy plane. So what should we write here is we could write we could write, let's say, E as a total of this triple integral and F and d phi. Now how should we write the D and the D inside the E? Because the D is the projection of E, which means D is area, right? D is area. So it can be dy dx or dx dy. So we could write now this becomes D, and the inside integral will be Z. So Z is U1 and U2. This is F, X, Y, Z, dz, dA. So D can be dy dx or dx dy. Or rather, not D, but the dA. So it depends on what we have in the information. Okay, now what's most important here is in this triple integral, in this general region, the first essential things is we need to find the upper and lower surface. This is for boundary, okay, for the boundary. And then to the sketch of D, okay, so again we need to develop D, and D and treat the d as double integrals, as usual double integral. Okay. Now, of course, by doing this d, we could have, for example, now we have the function of xy. So we have z function of xy, right, from this example. But of course, we could have another conditions, like for example, if we have y is the function of xz, or x is function of yz, that could happen too. So what if this happen? Then we just rotate the solids, and we could see that it could be, for example, for the, if z is like this, my drawing is bad, sorry. If this is d is like this, right, and maybe the y will be it will be like this, right? The y becomes the axis, the main axis, and x will be like this, right? It means that you can rotate this picture going to the right, going to the left, going to the front, okay? Depends on which one is the main axis. This main axis is C, right? If we look on the other example, it's to give more clear way for the D. So now we have the D is not just, this is just a general D that you can imagine which arrangement you are going to use, dy dx or dx dy. For this one, we have y equal function of x. Okay, so we are going to have, so we have first is, let me write the function of x, y, z, and first is dz because it's having u, right? And this will be dy because it's g1x, g2x, and having dx. This is x is maybe a to b, right? Okay. But I don't think this will be so what I want you to notice is it doesn't matter what type the E or D will be. For example, now we have this is, we call the type 1. This is a type 1 E, type 1 D, which means that it has a function of x for the D. We have also type 2, function of y. But for the numbering, type 1, type D, it doesn't matter. I don't really care the number, and I usually also forget the number. What the important thing is to set up which function it is. That's the key. So no matter type 1, type 2, or any type that you are need to look at, the key is always to set up the boundaries, set up the correct boundaries. This should be the key for every multiple integrals or every triple integrals you have. For example, you can have a, b, and then the second one is the same one as this. So g1x, let me just write as an example. And the last one is the function of two variables. And let's say this is the functions. You just write function as just f to make it easy to look on the other variables. Okay, let's say this is the first one. Okay, this is our D is this. Okay, now we could have also the other subject, which is CD, and let's say this is H1Y, H2Y, and this will be U1XY, U2XY. This is, let's say, same F, DZ, DX, DY. And of course, the last two here will be the D. Okay, so we could have two kinds of D and three kinds of the XY. So XY, YZ, XZ, that will be the function of two variables. Okay, and I think to make it more familiar, we need to have like some examples, right? And I believe just these two setup, it could brings you to more variations in the future. I think the key is just these two. This is just the key. Okay. The other variations is we are going just to look on the arrangement of the order. Okay. What type of functions you have. Like if you have the function of two variables is yz, then you need to set up in terms of yz, and the other part will be the other variables that you need to set up. Which one is the function of the other one, and which one is the constant, and that is how we set up the integral. Because if you have the textbook, your textbook is defining all these types in terms of the type 1, type 2, type 3, and I don't want to make these sections by memorizing the type. It's not important. Okay? The type is not important. So maybe another key is yeah, I think this three is just enough for the triple integrals. Find upper and lower surface, which means define the the function of two variables. Is it xy? Is it yz? Is it xz? We need to define and look on these functions as the upper and lower surface, and then sketching the D, and then we treat D as double integral, and we follow the rules. Okay? Which means if we are treating D as double integral, maybe at the middle of calculation we can also convert to polar, can be converted to polar if we need. Okay, so I just skip several parts, and from here you can imagine that if you want to have maybe a surface like this, then you need to imagine that maybe this is an x is function of yz, sorry, yz, and the other one is this here. This is xz. Okay. Okay. Maybe any questions? Any questions? Perhaps any confusions? So the setup for the integrals, for the triple integrals, we set up the outside as a constant, and then going the middle one is still the d. It should be function of, it's supposed to be the constant one, so g of x. So this is x, this is g of x, and the last one is the function of two variables, okay, of x, y, and it's supposed to be the z, right? Now I hope you can get the idea of this arrangement first. Okay, the arrangement. Okay. But let me go to examples. Let me go to example. Okay. We could write the evaluate triple integral. Let's say we have this e and then z dv. And then e is solid. Obtain, or maybe solid in the first octant. Bounded by the surface z equal 12x1 and planes y equal x, x equal 1. So first, if we look on the e, we know that this is the function of two variables, like for the z. So this will be function of x, y. So this is just the example as the previous one I mentioned. You have the z equal function of two variables x, y. Then we could set up the d. So we could draw the d. So we could have the y equal x as the planes, and we could project into xy plane. So since it's function of two variables xy, the xy will become our projection. Okay, become our projection. So this should be y equal x. Okay. And maybe this one is 1. So x equal 1 is here. Okay. So this will be our d. Now based on what we have, we could write the triple integrals for ZDV as, if you would like to start with x, okay, for the outside integrals. So we start from x, from 0 to 1. Okay? And then for y, we could start from 0 to x, right? As usual, as the double integrals that we usually did, right? So we could start the second one from 0 to not y, x, okay? And the last one is z. Z is from 0 to 12xy. And then the inside is c dz dy dx, right? Okay. Okay, we start from the inside integral. Okay, we start from the inside integral. This will become z squared over 2, and we can input the 12xy inside. Now it could be the 12 squared. 12 squared is 144 divided by 2 is 72. Let me write 72 outside. Okay, and then 0, 1, 0, x. This will be x squared, y squared, x squared, y squared, dy dx. Now, as usual, we could write this inside integral dy, so you should write x squared, y cubed, 3, right? From 0 to x, and then still we have this dx. Now we could write down x5, right? x5 divided by probably going outside here, divided by 3, 24, right? 24. Let me write this 24. So we could write down this should be the x6. So this should be 4. Okay, that's our calculation. Okay. Okay. Maybe questions? Let me give you another example. Let me give you a little bit complex one. Evaluate triple integral E is bounded by y equal x squared plus c squared, y equal 4. If you want to draw, like imagine how it looks like, we can draw the paraboloid. This is paraboloid with the main axis is y. Okay. And we can try this one. Okay, let me help the drawing. Let's say we draw, because I think we can draw the paraboloid easily. Not really that difficult. Okay, so we are having the axis for the paraboloid in y, right? So we could have the paraboloid on this, like that. Yeah, probably like this one. Okay. And then we have this is at y equal 4, right? And then we have our projections on the xz plane. That is from here, right? Oh, too big. Okay, that's our projections for the xz plane. So we could start with imagine the what's the order of the integrations, right? Because we start with y equal x squared plus z squared, then it should be start with dy, okay? And then it can be dx dz. But let me just start with dz dx. So the outside integral we will have the x, which is going to be here. Okay, it's going to be because uh, the circle equation is x squared plus c squared equal 4. So we will have the radius is 2. So we will have negative 2 and 2. So here is the 2 and negative 2 for the radius. So we could start with the integration from negative 2 to 2. And how about the z? Z itself we can write down is 4 minus x squared, but it's plus minus. So we could have the positive 1 and the minus 1. So we could write the triple integral as so let's say dy, dz, dx. And dz will be from the negative, right? The negative of 4 minus x squared. This is 4 minus x squared. And then dy is from the paraboloid until 4. Okay, that's the maximum endpoints for the plane, right? The y equal 4. Okay. The inside one is easy to calculate, right? Because it's just dy and there is xz inside, so we just plug in y here for the integrations. And for the outside integrations, I think this is the complex one. That if we see that, because it's a circular, remember that we can convert this, we can convert to polar. But let's say we are going to solve the inside integral first. Okay, let's say we are going to the inside one. Okay, so we still write so this will be y and then x squared plus c squared, x squared plus c squared, 4 and then dz dx. And this is going to be this is 4 minus x squared plus c squared. Okay, now it looks ugly, right? It looks really, really bad. Now, from here, we can convert to polar. So if we see that the polar will have the circle is x squared plus c squared equal 4. So r is from 0 to 2, and the theta is from 0 to 2 pi. Okay, because it's the perfectly circle centered at 0, 0, right? Unless you want to change the center, and it will be different theta. So we can write down the polar, convert to polar. So convert to polar, and becomes 0 to pi and 0 to 2. This one is 4 minus r squared. And square root of x squared plus z squared is r, right? It's r. And don't forget to multiply with another r squared, dr d theta. And I think this pretty much easier, right? Pretty much easier. So we could have 0 to pi so we could say that this will be 4 over 3 r cubed so 8 what is this 8 32 over 3 32 over 5 32 3 6 256 over 15. Yeah, I think this will be the answer, right? Or if I have mistake for my calculations. Oh, wait. I think I've mistaken here. So 32, 5. Oh, it should be minus. Sorry. 54. Okay, that's the second example. Oh, it's not 5. Sorry. So it should be 6. So it should be 1, 2, 8, 15, 5. Okay. Okay, any questions? If no, I will continue to the next section. And don't forget to check the Moodle for the quiz, okay? Okay. Okay, last sections. I hope still have time. Let me just write down the topics. The topic is how to change the order of integrations. And this topic is, I tell you beforehand, it's difficult. Okay. So let's say we have the integral, the triple integral, 0, 1, 0 x squared, and 0 y. And then it should be fxy d dz dx dy and dx. And then rewrite triple integral the first one is write down dx dz dy, the second one dy dx dz. Now to begin, we could start with just write the as in E. Okay. Now we could write down the E. We could see like each one is having its own setup for the integrations. So x is from 0 to 1, and then y is from 0 to x squared, and z is from 0 to y. Okay, if you want to look at what is E and how we can draw the E, we could look at this graph here. It's a little bit complex, but if you take the focus on from x and then y and then z, we see that from x we have 0 to 1. Okay, we have this. Okay, this is our the point that we are going to evaluate. And then we see from y, we have this is x equal 1, and this is y equal x squared here. Okay. Now we have z equal y is on this section up here, right? So z equal y is if we project into z equal y, this is our line, right? And then we need to project this line into this sides of the solids, and this will be our z equal y. Okay, because z equal y is a plane, right? It's a plane like that. You to imagine that it has a long plane like that, right? Okay. Okay, now from this figure, we could write the projections. So projections the projection on xy plane, if we see the xy plane, we could see the d becomes xy 0 to x to 1, and then 0 to y to x squared, right? If you look just xy plane. But we could also exchange this d, and we could see from y, from 0 to 1 here. We could write from there So we need to express in different variable, right? And we could express the x from this curve to this, right? So we could write down from square root of y through the 1, right? Okay. I think no problem for this one, correct? If not, then you can try to imagine like we did in the double integral. And if we take the YZ plane, so perhaps to help you get correct answer, you need to have good visualizations, okay, good imagination on the solids, okay, that it could help you. Now in the YZ, so YZ here. So we could start from Y is from 0 to 1, right? From 0 to 1. And then from Z is from 0 to Y, right? So if we take this Z till here, so this is 0, 1, okay. And then 0 to, this is equal 1 to Y, right? Okay. Now we could express in different forms. So let's say we are going to express from Z, 0 to 1, right, for Z, and then for Y will be from Z to 1, okay. Okay, I think also not really a problem, right? And then the last one, we have XZ plane. We start from XZ is we start from 0 to 1 for X, okay. And XZ is, the other one is from 0 to the X squared. Okay, this is from this part here, small part here. This is the XZ, and we have another one is here, projecting to XZ plane. Okay, I hope you can see. So it start from here, the x squared, y equal x squared, and then it's projecting through here, and then it's projecting through here. Okay, I hope you can see that part. So that's why we have this x squared, z equal x squared is from here. Okay, and then we can change the variable. So we can say z is, let's say, from 0 to 1. Okay, let's say 0 to 1. And then for x is from 0, or from this, because 0 is here, then we start from this line until this one here, right? So we could start from square root of z, square root of x, and then less than 1. Okay. Now, if you would like to draw separately the projections, we could also do that, and this will be the drawings for each projections for xy, yz, and xz plane. This is what we have. Okay. And then we can describe the solutions. Okay. So first, the solutions is we would have we would have, if we would like to make it into dx, dz, dy, so we will start from y, that is, y should be a constant. So we could look on this, right, from 0 to 1. So 0, 0, 1, and then dz, dz should be having a function of y, right, because it's the outside is dy. So we could write dz 0, y, and then squared y and 1 for x. And then the other part, dy, dx, dz. So z is start from 0 to 1 for z, right? And the functions of function of z related to y will be square root of z. Function of x is z, which means this is z, and then 1, and then dy will be from z to the x squared. Okay, I think we can discuss this a little bit more later in the Friday class, because I think the time is up for today's class. So, okay, don't forget to click the quiz, work out the quiz, okay, in the model. Please check the model. I put the quiz in the weeks, okay, so you can check the week 16 May and then 22nd May. You can check, there is one announcement about the quiz. Click the link and you can work out the quiz, okay. Okay, if there's no questions, you can leave the meetings, or if you would like to scan the QR code, you can scan the QR code. Okay. I will discuss more about the change of the order of integrations in the Friday class. I believe it's a little bit complicated because you need to imagine to project to 3 different sides, right? You need to project through xy plane, xz plane, and yz plane. Okay, if there's no other questions, you can leave the meetings, and see you on Friday. And hopefully you already finished the quiz, okay? Because the deadline is Wednesday. So before Wednesday, should be finished the quiz, okay? Yeah, you're welcome. If you have anything to say,